Welcome everyone. So tonight, this is kind of like a lot of people come to this because you make art and computer art and things like that, and filmmaking and gaming and TV and everything like that. But who makes all that stuff that allows you to use that gear and that technology, um, and the software? So tonight, these are the questions that kind of spawned a couple of our members, and then they went to grad school and started researching this kind of stuff. So we have two people with different experiences that are going to talk about what they've done um, post undergrad and continued their education into the art world, but behind the scenes, basically. Jackson's a little different. But Jacob's gonna start. So, uh, Jacob, take it away.
Okay, hello. My name is Jacob. I'm currently a student, and well, let me bring up the slides before I start talking. That's probably a good idea. But I'm a student. I'm a graduate student studying computer graphics at University of Pennsylvania in Philadelphia. Um, and can okay, wait, sorry. The audio, I have to press a button, I believe. So let me press the button. Also, Jackson will be in the chat. So if you guys have any questions during either one of us speaking, you can put them in the chat, and whoever's not speaking will answer the question. Okay, cool. So we're going to start with a short video that is kind of a behind the scenes of Interstellar, because it's a great example of kind of this intersection of science, technology, and art. So if this is not audible, make sure someone says something, but here we go.
The initial impetus for the project had been to say, why not examine real possibilities? Why not actually look at the real science there?
Luckily, we had Kip, and Kip is the foremost authority on all things gravitational.
The warping of space inside here scatters some of it back, light scattering off of the surface of a rippled ocean.
Neither wormholes nor black holes have been depicted in any Hollywood movie in the way that they actually would appear. This is the first time the depiction began with Einstein's general relativity equations.
The visual effects department under Paul Franklin and everybody at Double Negative took Kip's mathematical data and they created real visual representations of what a black hole is meant to look like.
The collaboration has produced visualization of things which nobody had ever managed to do before. We potentially may have discovered a couple of new things that were lurking there inside the mathematics, inside the physics.
I worked out the equations that would enable him to do the gravitational lensing. And so you have light that comes from a star behind a black hole. It may come in, go around the black hole several times, and then come to the camera. And so you wind up with several different images of the star.
The black hole warps the space so much, it just looks like you're looking at a strange sort of funnel in the sky with this intensely black circle at the middle of it. But the gravity of the black hole draws in all the matter from the surrounding universe. And this spins out into a giant disk around the central sphere. And as it whirls in towards the center, the gas gets hotter and hotter. And this thing, the accretion disk around it, shines brilliantly. And then we found that if you then render this whole thing, you visualize it all through this extraordinary gravitational lens, the gravity twists this glowing disk of gas into weird shapes, and you get this extraordinary sort of rainbow of fire across the top of the black hole.
And I saw this disk wrap up over the black hole and under the black hole. I'd known it intellectually, but knowing it intellectually is completely different than seeing it, than feeling it.
We had determined when we started down this road that if it didn't look like something that would be comprehensible to the audience, we would have to manipulate it in some way. But what we found was, as long as we didn't change the point of view too much of the camera position, we could get some very understandable tactile imagery from those equations. They were constantly surprising. Spoke to the maxim that, truth can be stranger than fiction.
We're going to write several technical papers about this. One aimed at the astrophysics community, and then something for the computer graphics community, saying, here are some things that we've discovered about gravitational lensing by rapidly spinning black holes that we never knew before. So this collaboration isn't over until we've given some sense of the things that we've learned.
Okay, so that is exactly kind of the intersection that I am most interested between art and real kind of physical models. So they showed in that video kind of the director and then this guy who is really a physicist. And what my kind of role is, what I'm interested in, is kind of right in between those people, kind of mediating that conversation. So I wouldn't fully be kind of in either domain. I would be able to kind of translate back and forth in a way. So so that kind of gives you an idea of kind of the role that I personally want to play. So I went to Ithaca College. I got a undergraduate degree in film, and my senior thesis relied heavily on 3D animation and visual effects. And so around the last year and a half of school is when I really started exploring like what I could do with art while also incorporating a lot of this kind of technical kind of proficiency that I really wanted to have. For a lot of my life, honestly, I wanted to kind of combine those things. And so I went out and lived in LA for a couple of years, and I realized that I didn't feel like I was quite where I wanted to be. So I came back to the East Coast, and I moved to Philadelphia. This was before I had any plans of going to Penn. And after several months of being here, I started researching some graduate programs. At first, I wanted to do math. I was like, I want to just totally switch it up and apply that in some way to art, but more as a side effect, not as the purpose of the program. But then I saw that at the University of Pennsylvania, they had this program called Computer Graphics and Game Technology. And so I saw that, and I realized that there was this perfect kind of the way the program director described it was getting under the hood of animation. And so it had this kind of direction, it had this kind of focus, and it also on art, but it also had this heavy technical side. And it actually takes place in the engineering school, so it's definitely it's an engineering degree, but it has the purpose of serving art. And so on the right, just so you know what this picture is, on the bottom, that's for my senior thesis. I had to rig and animate and do a lot of from scratch work, or at least I chose to for my film, with the help of my professor Brad and Shayna, and I couldn't have done it without you guys. So in the top picture is me in high school. So or it looks like perhaps somebody from the 1970s, either one of those. But so I had no math or computer science background, and so when I enrolled, I kind of was met with a little bit of skepticism, especially since I really just kind of decided in a very well. The way I kind of went about it was I learned about the program. And then I probably an hour later drove down to the school and found where the program director's office was and knocked on his door, and he wasn't there. So I knocked on the program director assistant's door, And I went kind of down this line of doors until I found the door that opened. And then when I found the door that opened, they gave me the key to all the other doors, so to speak, and they kind of helped me work on a resume to apply to the school. And so I did, but again, no math background. So most of this was motivated by my art background. So they had me enroll in the MCIT program, which is a computer science master's degree for people that don't have a background in computer science. And so I went from kind of ones and zeros, literally, to pixels on a screen to making images. And I'm in my second year, and my interests right now are physically based animation. So that's going to be like simulations and stuff you would do in Houdini, which is a procedural VFX program like water and fire and gas and these kind of things. And then I really enjoy geometry. So the model they introduced me to when I first got to Penn was this kind of model of engineering as a series of black boxes. And so when I took this intro to computer systems program or course in my program, we literally started with binary. We were literally adding together binary numbers that represented decimal numbers, like converting them back and forth. And then we ended up all the way into making that into a CPU. So kind of putting transistors together, making logic gates, programming in ones and zeros, programming in assembly, which is one step above ones and zeros, into C code, which is kind of the predecessor of all modern programming languages. I mean, there's probably some nuance there that I'm not fully aware of, but that's kind of a kind of broad overview. And so I learned this abstraction model. And the model is that we start at the bottom of this pyramid, you can see with transistors and electricity. And then we kind of put them, once we kind of figure out how we're going to use them, we put them in this black box. And what that means is instead of transistors and electricity, now we're dealing with an input and an output. And so we know we can put something in, we can put numbers in and outputs the answers to mathematical equations, for example. And then you can kind of work up the chain until all of a sudden you're at this level where you've abstracted from transistors to gates and memory to a programming language where you don't know exactly what's going on all at the bottom level, but it's all kind of in this black box that you don't necessarily need to know exactly what's going on. And if you had to, then you would literally have to know everything about a computer to even write one line of code. And that's just not necessary. And that's kind of how we're able to build knowledge without everybody having to know everything. We kind of describe things as functions, as an input and an output. What goes on in the function is kind of dependent on what field and what purpose you have. So once I got into the CG program at Penn, then I started studying more mathematical topics. Most of those consisted of linear algebra, trigonometry, and calculus. So we're dealing, and as far as all that's concerned, the real specific part that is most relevant is going to be matrices multiplying vectors. And what that means is you have a point in space represented by a vector. Vector is going to be x, y, z. And then you have a matrix that is going to represent kind of a transformation on that vector. So let's say you have an arm and you want to rotate it like that. This arm is a set of points, and you're going to rotate all those points up, with reference to the elbow like that. And so the way that's done is by applying a matrix and then multiplying it by all those vectors that represent all the points that is the arm. So that's kind of the basis of everything I'm doing. And then you get into more complex models where you're dealing with quaternions, which sounds like a super complicated word, but my teacher always told me that it's all notation. It's not as complicated as it seems. And honestly, once you get the notation, then all these symbols, they don't seem like a different language because they're not a different language anymore. They're a language you can speak now. So it's not that it's very technical, but I learned how to speak in a technical language, and so now it's kind of a lot more natural. And so the programming is going to be a lot in C++. We're going to be writing shaders. We're going to have kind of data structures describing 3D objects like a question like, how might you represent this sphere on the right? How might you represent that? And so you have to come up with kind of data structures that are going to be stored in the computer and represent that structure. And because we're doing a lot of stuff around graphics, that's a lot of the kind of data structures we're dealing with, are like meshes, implicit surfaces, which are more mathematical. Okay, so let's talk about the intersection of art and technology a bit in a more philosophical way, because I think that is doing it at this kind of high level is going to be a little more interesting for everybody. So I kind of came up with three general models to kind of look at this intersection, this way that we can communicate between what seem like two different worlds. And I kind of have arranged them in such a way that maybe if we look at it from many different angles, we can get a better idea of what's going on. So there's, let's call this the information chain model. And so what this is representing is kind of this linear, this line where on the right side we have things that are more scientific, more technical, physics. And then on the left side, we have things that are artistic and kind of expressive and creative and rely on these other things. But as you can see here, there's this kind of dependency chain. So on the right, let's say we have what is. So these are just things that are. The world, the way water works, the way that electrons move, all these things, that's just what is. And physicists take what is and they put it in mathematical models, but it's still very low level. It's still very tied to physical reality. And then we kind of move up this chain where we go to computer science. And so computer science is going to be informed by physics, but it's not physics per se. It's using parts of physics and putting them in kind of this black box, where to be a computer scientist, you don't need to understand everything about physics, but what you're using can still be based on it. And then visual effects is informed by computer science. Every visual effects artist doesn't have to know how to code, but all the things they're doing have kind of this coding literacy built into them. You're interfacing with programming. And I like to say that anybody that uses a program like Maya or Houdini, even if they don't write a line of code, you're still programming. And the reason I say that is because programmers might write lines of code dealing with specific variables and a syntax, but when you move a slider around, you're programming. You're doing the same thing. You're just doing it at a level that is more, let's say, artist friendly. And so you're kind of at this higher end as a visual effects artist of programming. And so it's going to be more abstracted, though. And I'll get into kind of exactly what abstraction means in the next slide. And then at the end, we have filmmaking. And so filmmaking is kind of the end of this chain. It's informed by everything else. It uses everything else. But again, it's its own thing. But the thing is that this isn't a one-way path. We have filmmaking also being it's at kind of this end where we're deciding. So physics is informing from that end, while on this end we have art deciding. And when I say deciding, I mean that filmmaking is going to decide how to use visual effects. It's going to decide what visual effects are needed. And then visual effects are going to decide what computer science is needed, and so on. So that's why I kind of represent it in this way, where we have what is and then what is needed. And so we have people that take what the world is, and then we have people that apply that to specific projects. And I have CGGT in the middle, because that's kind of where I live. That's kind of my domain, is to be kind of in the middle of these worlds, right in between visual effects and computer science. And so I also have this kind of model that is an abstraction kind of hierarchy. And I put this in 2 dimensions with kind of jagged shapes, because I wanted to show that it's not quite as linear, it's one-dimensional as it might seem on first glance. There's aspects of each field that are more or less abstract than other aspects. But generally speaking, if you look at this kind of key here, the red dot is an interface, and I'll describe that in a second. So we have, again, filmmaking on this end and physics on this end. And when we say abstraction, what we're talking about is what I was saying before, which is we have this paradigm that deals in specifics, and then we generalize it so that a step up the ladder can use that without having to understanding all the specifics. So a physicist sees atoms in the world and they say, well, I can't track every single atom. Where is it? But what I can do is generalize that into something called pressure or temperature. And those are generalizations of very, very small and numerous objects. And so even physics is abstracting. But then what we're going to say is that a step up from that is computer science. And so computer science has this point of interface between computer science and physics is, let's say it's electrical engineering. It's this point where we abstract certain aspects of physics so that we can use them for this domain of computer science. And then computer science will, cover a broad base of things, but then we can use computer science to interface with visual effects. And we get kind of this graphic programming, kind of programming shaders and specific things. And then we move up, and visual effects can turn into film in the sense that it's just animation. So animation is perhaps a more kind of low. I mean, you could, if we're going to use this kind of paradigm, we would call it kind of a lower level kind of filmmaking. And when I say higher and lower level, I'm talking about kind of lower level is kind of the nitty gritty, and higher level is where you kind of are generalizing that for your purposes, so you don't have to understand all of it, but you can still use it. And so we call that an interface. So if you had let's use the atom example. If you had a ton of atoms and you wanted to describe them, you describe them as pressure, and now all of a sudden you have a slider on a screen where you can increase and decrease pressure. And it does something under the hood with the atoms, but all you need to know is we're dealing with pressure. So, and here's one, this is the last model that I kind of made, which is this representation model. And this is, I think, quite interesting philosophically because, so we're starting with the world as we observe it, we're making a mathematical model of it, then we're kind of discrete, with a computer, we're kind of just discretization of these kind of things in the sense that it's literally binary, it's ones and zeros. We're turning the world into these discrete objects. We have a continuous world, but in order to understand that world, we have to turn it into something we can put in categories and that we can kind of make into their own separate things. In reality, nothing is separate if you really want to interpret it that way. But for the utility of human beings, we kind of turn things into human, understandable, and things that we can work with. And so in a computer, we're going to kind of reconstruct this model of the world. And then I should say also something interesting about that discretization of the world is that it introduces an error. It's not exact. When you try to turn the world exactly into discrete objects, you actually lose some information. You can see that in kind of, let's take a water simulation where you're simulating particles. You aren't simulating the continuous trajectory of those particles. You're sampling it. If you ever heard of sampling, you're sampling at different points. And when you sample, you kind of lose some of that information in between. But there's no other way for a computer to understand something. And so at the end, we visualize into this kind of model of the world we started with. So we kind of start with the world, and then we reconstruct it for ourselves in a way that is understandable to us. And then I also introduced this kind of thing on top, which is feedback. And the question becomes, does that visualization, does that representation that we create of the world turn into the world itself? And so I created a class project. I'm going to kind of blow through this because I need to wrap up for Jackson. But in my class, I'm developing a plugin in Maya that it solves a problem I had as an artist. It solves a problem, which is that Maya didn't have a certain tool. And so I started as an artist, and then I realized, you know what? I need this tool as an artist, and so I'm going to create this tool. And so I'm creating this simulator for Maya based. And so what that means is I had to learn how to do that, of course. And so I had to dig deeper. I had to go deeper. I couldn't just deal with abstractions. I had to go into a deeper, lower level of information, which is all these, math symbols and everything. I did have to understand to an extent what was going on under the hood, in order to kind of bring this up into a program that people can use. And so I had to make a literature survey. I had to read all these papers. And so I'm trying to work on a kind of new approach to it. So, but the way I'll end it is that I would say the point of this is that my artistic experience informed this entire process. I didn't start as a physicist or a scientist. I work from the other end. And so I kind of want to express that this isn't a one-way street. You can start at any point on the spectrum, and based on your need, you can end up wherever you want. As an artist, I have a unique perspective that I use the tools that I'm making in school. And so I understand them at a different level than some of the people that know it at a lower level. And knowing all the nitty gritty doesn't necessarily mean you know what a user wants to do with it. And so I have a different perspective in that sense. And so my advice is to do what you enjoy, and it will lead you naturally to the level of abstraction that you want to live in. And like I said, we're all programmers in different levels of abstraction, and solve the problem that you have. So before you have the problem, maybe don't get into this level of math and all this stuff. But when you see the problem, then you can try to solve it, and you can learn exactly where and what domain you want to live in order to solve it. And so with that, I give it to Jackson.
All right, can you guys hear me?
Yep.
Okay. Yeah, sorry, I was having some technical difficulties before, so you guys are seeing and hearing me through a different computer, but as long as you can hear me. I'm going to share my screen, and I'll pick up where Jacob left off. Can everyone see that okay? Great. Awesome. So my name is Jackson. I graduated from Syracuse back in 2018, which is crazy how long ago that was. And during at Syracuse, I actually started as a film BFA student in VPA. Um, I originally applied for all of my schooling and stuff as a film student, and that's what I was 100% convinced I wanted to do in life, was study film, and from there, go into the film industry in some capacity and just, make movies, make something fun. But oh, and also that's when I first met Shayna back in fall of 2018. Been going to SUP for almost 8 years now, which is crazy to think about. But um, but basically, as I was going through the film program, um, I started to notice some things that I'll talk about a little bit later in this presentation. But um, I kind of was noticing that I was gravitating towards more specific parts of film rather than others, and that eventually led me to change my majors entirely. So I ended up graduating with a degree in applied math and neuroscience in the School of Arts and Sciences. And then after that, I went to grad school, and I just finished up in December. I did my master's in applied math and stat at Johns Hopkins in the School of Engineering. And within that program, I kind of focused in on statistics and statistical learning. That was a program where I had to do a thesis. So my thesis was called Delayed Acceptance Simulated Annealing Markov Chain Monte Carlo Methods in Neural Architecture Search, which all you need to know about that is that I was basically automating the design of neural networks using probability theory. And basically from there, I've been doing just a lot of random research things, both research assistantships in undergrad and grad school, and just a lot of different, I've been touching on a lot of different areas, and I'll get into more of that in just a second. But I think the first major thing I want to address is, why did I actually switch from being a film major into this much more technical kind of like field? And what I noticed when I was going through film school is that I was much more interested in like the technical aspects of filmmaking. So I found it much more interesting to focus on the like image codecs that were being used, how to optimize image quality, how like the actual color grading software and editing softwares work. I found myself much more interested in that stuff than the actual like producing a final output film, for example. I found that it's still interesting, don't get me wrong, but um, I just found that sort of like technical like aspect of it very interesting. And at the same time as when I was in my film program, I was taking math classes. And so I eventually decided, I think something closer to engineering, but still letting me explore math and stuff would be just like more fulfilling as far as what I wanted from my academic experience. I also kind of levied a trade-off of I can do film stuff outside of just academics, right? So like I can support my previous classmates in their like thesis films, for example. I can work with people to just do random creative projects that would let me keep that side of what I was interested in while also going down a much more technical route. Kind of on a funny note, my parents were actually disappointed that I switched out of film, which I think is kind of the opposite sentiment that you would expect. Um, they wanted me to stay in film for some reason. So, uh, yeah, a little bit of a fun note. But I found the math coursework much more fulfilling. And I eventually went into this little train of thought where I thought I was going to go to med school. So I started working on ambulances, and then I added a neuroscience major along with the applied math. And when you're preparing for med school, you need to get a bunch of like kind of prerequisites done, like clinical time, research time. And through that is where I actually fell in love with research because I joined a research lab. And that's when I really found that like research is the thing that I really enjoy. And so after kind of deviating from that course, I then decided I think grad school is the more appropriate path for me rather than strictly like med school or something. And then I just put some pictures of random stuff I've done. I still try to do some film and photo VFX stuff from time to time. Um, so yeah, a little bit more background about me for research. So in undergrad, I basically did a lot of stuff to try to figure out what I like. So in undergrad, I did independent study where I was looking at mathematical signal processing. That was stuff like Fourier transforms, wavelets, things that have to do with any sort of like image encoding or sorry, signal encoding or processing. Um, I did a capstone project that had to do with chroma subsampling. I actually presented on that at SUP back in I think 2022. Um, and that was kind of an adaptive chroma subsampling scheme where if you guys are familiar with chroma subsampling like 420, 422, 444, the idea was to make that an adaptive process where it's not the same throughout the entire image, which could potentially let you compress more of the image while keeping some of your more detailed regions less compressed. And so it visually look better and be more effective for things like green screening. Um, but on top of that, I went did the a pharmacology lab at SUNY Upstate, which is right across from Syracuse. The Syracuse people probably know about that. There, I was studying sudden unexplained death and epilepsy, and a lot of the work there was cardiac signal processing, so ECG signals, EEG signals, pulse oximetry, just anything that was a signal that could give us information about what happens around the point of a seizure. Um, and so in grad school, I then went to cybersecurity, which was a little bit of a pivot, but I was always interested in cryptography. So the research assistantship that I did was through the Hopkins Information Security Institute. We competed in a competition ran by DARPA for the U.S. Department of Defense. And that was a challenge called AIXCC. It was a competition between, I think, 7 teams trying to develop the most innovative generative type AI models for vulnerability detection and patching. So basically what we were trying to do is how can we create systems at scale that effectively find and patch vulnerabilities that are previously unknown in computer systems. On top of that, I also did work on my main thesis that I mentioned before. That was primarily kind of like the intersection of probability theory, machine learning, and what's called Markov chain Monte Carlo, which is essentially random sampling using Markov chains. That thesis was kind of I'll talk more about it later, but so why did I choose my school is kind of where I want to go with this. So there's a lot of considerations for when if you want to like kind of branch out beyond film and go to grad school for something more like harder STEM. Stuff like faculty, facilities, the actual like research institutes and research areas that are available at the school, what the coursework looks like and what the requirements are. Those were all major things that drew me. Um, and I also noticed that a lot of the courses have to do with projects, and that would let me actually like insert some film stuff at the same time. Because a lot of what I like to try to do is I keep film stuff kind of like on a tangent, like adjacent to the stuff that I'm doing, so I can keep up with it and keep enjoying it, but focus on other things as like my main activities. So like for an example course project I give here with all the cat images is there's a method of image upscaling called Markov random fields. I basically, one of my course projects, I modified an aspect of that specific algorithm to use neural networks instead. And basically did a comparison of what it looks like with and without that kind of neural network adaptation for what's called a message passing function. And that's just kind of a display of the results that it does pretty well. And then the pictures below that was, again, you'll see a trend inserting machine learning into random algorithms. This was inserting neural networks into a specific rendering algorithm. So instead of doing just like a specific type of random sampling for each of our points, when generating our image, it follows like some sort of training, and that's a sample render using that method without getting into too much detail. So now I'm going to talk a little bit about kind of grad school and what options are available if anyone is interested in kind of pursuing something more technical. Both ways that you could just go fully dive straight into it, or you could kind of like dip your toes, kind of like what I was doing by doing a master's first, of kind of dip your toes and see kind of what you're most interested in. So first, I'm going to talk about some imaging science specific programs that exist out there. Not a lot of people know that these programs exist because it's such a niche field. And there's only 2 schools, as far as I can tell, in the country that offer an imaging science specific grad program. But that's RIT over in Rochester and Washington University in St. Louis. So they both offer master and PhD programs in imaging science. These are going to be programs that are a little bit more technical than what Jacob's program is, and the types of programs that he described, where it really is at the interface of engineering. But it's going to be a good mix as well of more applied classes, along with the more like math and technical programs. So RIT is a really cool school, to be honest, with these programs. They offer both imaging science and color science programs, depending on what you're most interested in. The imaging science program is a little bit more electrical engineering adjacent, whereas the color science is a little bit more like psychology, like neuroscience adjacent as far as the technical backgrounds. But they're both really fascinating programs, and I've considered going to both of them a lot. The Washington University in St. Louis program, the other imaging science program, it tends to be a little bit more biomedical imaging focused, like a lot of microscopy and related like medical imaging things. But they also do some stuff with more traditional like photographic imaging, things that could be film adjacent. Some other schools I kind of wanted to talk about and mention were UT Austin has a really cool lab called Live. It's the Laboratory for Image and Video Engineering. They do a lot of really interesting work with photographic imaging specifically. So, like thinking like image compression, imaging related tools like data transmission for video and film, things like that. They are one of the few labs that are dedicated specifically to that type of research. A lot of other labs that deal with imaging tend to encompass a wide range. So, for example, the institute at RIT could be anything from radar and LiDAR to photographic imaging, to just basically it covers a much wider gamut of technologies. But the UT Austin one's much more focused. And then another notable program is at Carnegie Mellon. They have a computational imaging lab. That one deals with more of the backside of imaging. So instead of like making devices and working with the actual like optical and physical components, more like algorithms for image processing. So like think like how your iPhone does its sort of like denoising and image upscaling, things like that. The picture that I have here is an example of one piece of work they did where they were taking regular video of traffic and they were converting that into real-time tracking data across 4 dimensions that they can use to train autonomous driving vehicles, basically provide training data on what traffic flow looks like for these systems. And so the next thing I'm kind of going to talk about is how do you actually pick a focus, right? So like say you're interested in going deeper beyond like studying film and you want to study something similar to what me or Jacob are doing. There's so many choices and every choice is different. So for example, UT Austin, the one that I just mentioned, I think a lot of people go into that from the electrical engineering degree program. There isn't a specific degree program here in their live lab that like is for that specific laboratory. So you have to come in either through computer science, electrical engineering, physics, etc. And so you kind of have to make some choices there about what program you're going to actually choose. And I think that the best way to start is pick something that you're interested in and just kind of explore from top to bottom as best you can. So like I give an example here of like image capture, right? Like just as generic as possible. I take a picture with my DSLR, what happens, right? You kind of have these core components, and Jacob was kind of alluding to this as well, is like the initial part that you're interacting with is kind of like the sensor, optics, the physical device, right? So that's going to fall more into like electrical engineering and physics, like how is light captured, how do photosites work, how is all of that actually integrated together. From there, you actually have the processing and coding, and that one's going to be kind of a mixed combination of both computer science, computer engineering, and electrical engineering, where you have certain physical parameters like processing power, storage space, processing speed, like how fast can you actually write data, like things like that make a big impact. And that's before we even get to anything digital that would be meaningful to a end user. So like how do we actually encode and transmit that data that we get from our sensors? How can we do that efficiently and safely so we don't lose any data? Um, that kind of falls more into that computer science, computer engineering, still adjacent to hardware, but not super in the weeds of algorithms yet. From there, we have what I didn't know what to call these exactly, but we'll say kind of post-processing-ish. So it's basically like, how do we encode our data? So like, okay, we now sent our image information from the sensor to some storage device on the camera, right? So how do we encode that in a way that we can then transfer to the computer? How do we make it so it doesn't take up an obscene amount of space on our computer? How do we represent the color properly? So all of those type of questions is where you're going to kind of fall into that's like really into codecs. Like, are you going to be in a JPEG or a PNG? Those type of questions. That's more like computer and imaging science. Those are more of the questions that you'll kind of see in more like computer based like processing, programming like aspects of it. And then the final integration of like, okay, we have some file that we recorded with some parameters, right? What do we do with it? Are we gonna make it into a movie? Are we gonna have to like downscale it? Are we gonna like cut it apart, color grade it, etc.? That's where I kind of like put into our more like film media studies, where what are you gonna actually do with what you just captured? Are you just gonna let it sit on a computer and no one ever sees it? Or are you gonna, make some interesting final like output? So that's kind of how I was thinking of like pick something that you really find interesting and like go through with it. So like I went through this process with a couple different things when I was thinking about grad school. Um, and it helped me learn a lot about how I was actually going to like what I was actually going to do. Uh, and so from there, how do you pick a school, right? How does grad school work in that context? So let's see how much time I have for go. The main thing you want to figure out is what's your end goal, right? Like what type of career do you want? If you're going to try to go into the film industry and you want to like be, for example, let's say you want to be a colorist, right? I don't know if you need to get a PhD in color science to be a colorist, right? I would argue that that might not be the best use of your time. But if you're interested in, for example, making a software like Resolve or contributing to that, that's a different story. And I think that really having an honest conversation with yourself about what your end career goal is could be really valuable. Um, and as far as trying to pick a program from there, most programs have a handbook that describes like the exact requirements that you have, who's available for advising, what the specific degree requirements are. I recommend before you even apply to any particular program, read that front to back, because that'll give you a lot of really important information about what the program's actually structured like, what you can kind of gauge what they expect you to have as far as a background when you're going into it, etc. Um, and then, yeah, just make sure you really understand the program back to front. But as far as research goes, so like let's say you're going to do I'm going to do a program at RIT, right? Research the faculty. A lot of people don't really think about this when they're applying to these programs. They look at the name of the program and they go, oh, that looks great, or I think I should go study this. You really need to look at the faculty and the research output that's happening there. I promise you that your advisor will make or break your entire experience and make you either hate or love your life for the next however many years you're in school. So really make sure that you pick someone that not only you like enjoy their research and get along with, but make sure that like I mean, to put it bluntly, just make sure they're a good person to be around, I think that's extremely valuable. Um, and then kind of to add to that, the specific research area that you're interested in, slash like the program slash institute matters so much more than the actual university you're going to. Unlike undergrad, where most programs, like there's obviously better and worse programs, but you can kind of gauge how good a school is, like overall, as like a broad picture. There is still some nuance to this, obviously program to program, but I think in grad school, especially when you're going to dedicate this much time to research, you really need to make sure that the research there aligns with what you want. So like an example I have is like for some things that you would want to study in computer science, MIT might be an absolutely terrible choice for you, even though it's considered one of the best schools for computer science on earth, right? So like a smaller local state school might genuinely be a better choice for you, depending on the research output that they have there. They might have some guy that like invented some specific thing and is an expert on it and could help you really develop your career in the way that you want, where MIT doesn't have any researchers that will deal with that specific topic. So that's just a really important thing to look at. And on top of that, look at publications, look at what output comes out of that institution. And that'll give you a good sense of, for example, what projects are available. Most of the time, when you're going to be going into these programs, you're going to pick an advisor and they're going to kind of throw work at you. They're going to, like, you can choose your advisor roughly based on your interests, but from there, you're kind of their guinea pig. So they're going to give you specific stuff to do. And I think it's really important to kind of see what that sort of output looks like to see if you're going to truly enjoy the work or not. And then final quick note, funding is really important. Do not ever pay for a PhD. If you're doing a master's, try to find a program that offers research or teaching assistantships. I think that's pretty logical, but never, ever, ever pay for a PhD, especially if it's STEM related. It's not worth it. So, and then I'll quickly go through this. How do you pick the degree? There's a couple different types of masters. There's research masters, non-research masters, and professional masters. I'm going to focus mostly on the research and non-research because those are the most applicable to people coming out of college. Professional ones are paid for by your company generally, and you normally do it to get a promotion. Research masters are going to be, it's a degree that is kind of like a PhD super mini light. You still have to publish original research to graduate, and this needs to be like something that is truly original and contributes to the field in some measurable way determined by your committee. But that's kind of like the crux of the whole entire like program, right? Is preparing you to create this specific piece of work. Generally, you're going to need an undergrad degree or similar in that field to go into it because they kind of expect you to come in at a certain level. And your coursework is going to be very tailored to what you actually end up outputting. So like, for example, I was doing like, so there's you can go anywhere with applied math in the program that I was in. You can go into any little small nook and cranny, but my coursework was almost entirely statistics. You might as well call it a statistics and probability degree, because that's what my thesis was ending up dealing with, for example. So as far as non-research masters, these are going to be similar, but since you don't have that thesis component, it's a lot more flexible as far as how you approach it. So a lot of times it's a really good choice if you want to just get a lot more advanced coursework in something. It's always these type of programs can often be good too if you're pivoting into something new. So like, for example, doing a non-research master's might be beneficial to you if you don't have any background in like computer science, for example, and want to go into it. Like a research-oriented program might be challenging to do without a lot of prior coursework. And then these master's degrees are often, they overlap and are awarded to PhD students that don't end up doing the full PhD. So that's kind of my general advice as far as picking your degree. And then I had a fun little demo that I was going to do. Have you guys, I'm sure some of you are familiar with Infinite Craft. It's a game on the site Neil.fun where you drag two things together and an LLM decides what is generated from there. So I made a little mock version of it to kind of go through the process of how do we actually discover what we're interested in, right? So are you guys able to see this? Okay. So here's kind of our what I call VFX craft, where our goal is to make an imagelet. So we're going to make a LUT that we apply to an image, right? So how do we start? What components do we need, right? So like the first thing that I would like, I'm just going to kind of breeze through it so we have time for questions. But number and a rule, we can create a function, right? And with a function, we take a function, apply it over a grid, and we get a table. When we go, we add some interpolation to that table and we get a lookup table. And this is not the final video LUT that we want. This is actually going to be a lookup table, which is a computer science specific concept. So we need to build some other things to actually get to our full image LUT that we're going to be providing. So now let's move over to kind of our electrical engineering. How do we build a camera sensor, right? So we're going to need some photodiodes and combine that with a filter that gives us a photosite. Put that photosite over a grid and we get our sensor, put some light to that sensor and we get an image. And this image is not processed yet. It's just going to be a grid of a bunch of different pixels. From there, we have to provide some interpolation to actually produce our full color values here. That'll be our demosaic image that we actually get. From there, we need some way to represent this, right? So right now we just have it sitting in some specific data structure. So let's say we're going to add RGB and put that together. So now we have an RGB representation of our image. From there, we need to create another piece. So we're going to combine our color space and gamma, make a color profile. From there, we have our color profile. So our color profile could be like Rec 709, for example. Combine that with our representation, and we have an encoded image. Wow, like a PNG or some sort of similar output. Um, we combine that. So then from now we have some encoded image and we have a lookup table. From there, we need to make some sort of transformation. Like, what are we actually mapping? Like, between what are we using our LUT to map, right? So we'll do, where was it? We need to create a color transformation. So let's add two color profiles, and I'll switch between the two profiles to get a color transform. Add that to our lookup table, and now we have an image LUT. And then we apply our image LUT to our encoded image. So that's our fun little game of infinite craft. Hopefully that's useful to someone. But yeah, I think now we're gonna dip to questions if anyone has some.
Awesome. Thank you, Jacob and Jackson. That was great. Really love that. So
Does anybody have any questions?
yeah, I'll jump in real quick. Jackson,
Okay.
You mentioned the kind of never pay for a PhD philosophy and kind of pursuing assistantships while you're looking at these programs and fellowships. Do you have any advice specifically on how to like broach those topics or bring that up in the process of application? Or find
So
that
my
information? Yeah.
I cut out the first part of what you said. Could
Oh
you
no,
say
all
the
good.
first part again?
Yeah. So you're talking about how you should avoid paying for a PhD if possible, right? And look for assistantships and fellowships. In your experience, how did you go about finding those, securing those in the process of looking at schools?
Yeah, so a lot of that is just doing a lot of research on the program itself. If most programs that fully fund you just guaranteed will say it somewhere on like their program information. Um, some the funding is dependent on your advisor. So for example, you apply to the program, you go in, they're going to fund you for a little bit while you try to pick your advisor within a couple semesters. But once you pick your advisor, they become the financial support for you throughout this process in exchange for doing like research or et cetera. Um, so if a program doesn't explicitly give you funding just outright, it can definitely be beneficial to reach out to specific advisors and kind of see like who's looking for students. A lot of professors will put on their site that they're looking for students if they're like, actively looking for PhD students. Additionally, you can look at what grants were awarded by the university recently. So let's say I go to the page of grants and I see, oh, Professor XYZ just got a big like massive grant for some specific research project I'm interested in. There's a good chance they're looking for more PhD students at that point. So I think those are good starting points generally. But talking to people never hurts, even though it's scary. But asking questions is good.
Yeah, totally. I like how you mentioned too that the situation can change like once you're there too. Securing like research assistantship can open up avenues for funding once you're in the program. Well, thank you.
Yeah, exactly.
I didn't mention. I see from Brian in the chat. I didn't mention the actual job title. I think I just described it. Technical artist, technical director. Those are the titles that a lot of people end up with out of my program. And then, so technical director, they're going to kind of mediate the 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 more technical processes on a project. They might oversee them. They might kind of mediate them between the director and the people, the artists. It can serve different roles. It's a bit amorphous. Exactly what I would personally want to do right now, but those are some titles that I am aware of. So.
Yeah, and on top of that sort of that idea of like on film specifically, as kind of alluded to in the initial video that we watched, there's a lot of times consultants needed. That's the first one that comes to mind of if you really want to be involved in film doing stuff that's more technical. So like Kip Thorne, the physicist, consulting on the specific project of Interstellar and using his expertise for that. But on top of that, you have a whole industry of engineers and scientists and stuff that are making Premiere Pro, are making, Resolve, that have to design your Canon cameras. There's a whole branch of that, and a lot of that's built on other software from other vendors and stuff. Like there's a specific like Adobe didn't invent like XYZ format that they use generally, right? It's either taken bits and pieces from other technologies or they're licensing it from something else. So there's this whole kind of stacked industry, depending on what you want to focus on, of different roles that people need. All the way from like hardware, like driver level engineers working on cameras, to like there's jobs out there that do like image testing, like color image testing for Apple, for example, is one. Like you can test their devices and do something that's not quite as hard engineering. So there's a big range of them.
And even within TDs and technical directors, technical artists, like Jacob mentioned, there's a vast range of specializations. Like Jacob was talking about, like character based, like deformation, maths, but there's also people working on a simulation and more towards the engineering side or more towards the art side. So is this kind of huge spectrum within that description of technical artist or technical director?
I've got a question. I don't know if you guys can hear me.
Yeah, we can hear you.
Okay. Are you guys currently talking to like people in the industry to make sure you're on the right path? Because I know I found when I was in grad school, when I talked to people in the industry, I wish I'd done it earlier because I did it sort of more later, and they would mention programs I never even heard of or like things like that. And I know that was one thing. If I can go back, I would have maybe sort of tried to sort of have a better sort of layout of steps from people who were maybe had the job I wanted or above that in industries. I don't know how much are you guys talking to people just to make sure that you're not sort of too in the bubble, I guess, of like school.
Yeah, Jacob,
Well,
you got this.
for me, I mean, I guess an example of where I would feel like I should do something for the job market or something is maybe take some classes in data science or machine learning or something, just because it's very hot right now. Um, Having a good idea about how those things work is important. And so I've talked to my professor about kind of making sure fill some of those gaps. But for me, it's much more exploratory. So I'm not as I mean I'm strongly considering like staying in academia, uh, teaching, researching. So for me, it is less about kind of orienting myself for something I want to do, and more so kind of learning things that I can then use to apply to something. The something is less determined than maybe it would be for other people, but that's just where I'm coming from. So yeah.
Cool, cool.
Yeah, unfortunately, I'm not trying to get a job in the film industry, so I don't have a good answer.
One of the programs Jackson mentioned at UT Austin, an undergrad student of mine when I was a graduate assistant at University of Central Florida, went into that program and is working as a TD or technical or a rigging TD at Disney now. So I mean, there's definite professional, and especially because a lot of these are master's programs that are describing, where they're not necessarily a terminal degree. I think there are many people from these programs that go straight into industry and are more professionally vectored, where Jacob and Jackson seem more academically vectored, which is fun in its own right.
Yeah, I will say that some of the projects I'm doing, I think, are serve the purpose of being very resume kind of worthy thing. Like I'm the plugin I'm making is, I think, going to be a great way for me to kind of add something to my CV that shows that I am able to kind of apply a certain skill set. And I think that having a lot of projects that you're doing is very important. Not just what you're doing in school as kind of exercises, necessarily, and that's always been hard for me, is to do exercises instead of projects. So I'm already kind of, I like project oriented kind of stuff more. But I think it's very important for people to see that you're self motivated and that you can do something that is marketable or whatever, rather than just like, I know how to do this thing that everybody knows how to do, but I learned how to do it also, you know. So it's good to be able to show projects.
Another thing too is that schools like RIT tend to, since they're more niche and there's not as many like programs like that in the country, companies that are hiring for specific things that like the specific type of roles that would be outputted from those programs, they basically the programs tend to feed into these sort of roles. So like a good example is RIT's imaging science program at both the master's and PhD level really does feed into, for example, phone manufacturers like Apple and like Samsung and such, because they develop a lot of expertise in camera imaging systems, and that's like a big piece of kind of how they push their new devices. So they have a lot of financial incentive to try to get good engineers for that. And there's not many programs that teach that specific skill set. So some of these more niche programs really do help you place into specific roles.
Well, thank you guys. I know we're a little past time, but this was really great. I'm excited to see what you do next. Jackson has graduated, so there will be a new adventure soon. Jacob, still have time.
Oh
Plenty of
yeah,
time.
I keep adding time.